All right, I guess we'll get started kind of on time for once. So last time we were talking about scrolling, different ways of doing scrolling, and we were on the iPhone with the flick to scroll. That was weird. And the different ways that it shows what happens when you get to the end of the scrolling, but there's other ways of moving things around. On the iPhone, it does have a scroll bar kind of thing that appears in the margin. You can't actually tap on it when it looks like this, but it shows you, how far you are along in the document. So it has the elevator kind of mechanism. And then in things like contacts and other things where they're showing stuff in alphabetical order, you get this other kind of scroll bar where you can jump to particular parts of the alphabet. But, for some reason on other kinds of pages, it doesn't have anything like that. The phones, it was kind of interesting that there's these two totally different mechanisms, depending on the application. And you also have two-finger drag. Is that what you're going to say? Yeah, we're going to get to sliders later. Yeah. There's just one slide on sliders because they're all pretty straightforward. So I figured I'd cover all the scrolling stuff and get back to sliders. So the iPhone also, features this two-finger drag, so you can move up and down a little bit, even for applications that are using one finger. That would be mine, of course. One finger to point to things. And in some applications like maps and so forth, you can use two fingers to zoom and to rotate as well. And after the iPhone came out and this got to be popular, they imported this back to the Macintosh for the pad, and now that's everybody's favorite way of scrolling, and there are applications that let you do that on PCs as well. There's a variety of other scrolling mechanisms that have been available over the years. So one of them is this hand, and that dates all the way back to the original Mac Paint. So the original Mac Paint in 1984, was assuming you had pretty small documents, right? It wasn't like Photoshop where you're doing these enormous images. You were just painting small things. And so rather than scroll bars, it had this hand. And that let you grab a document and pull it around. And we can do that today in things like Acrobat. Still has a hand. And if you, click somewhere, then you can drag up and down. And whatever you click on, you kind of hold, and then you can move up and down. And it's pretty reasonable for small increments, but it's pretty tedious if you want to go a long way. On the iPod, of course, they have the original dial, and that was a scrolling mechanism, and you could scroll from one end to the other. It started off as actually a physical dial, and then it became a virtual, touchpad kind of dial, and then it disappeared altogether. Another kind of standard thing to do is to tap at the edge of a reader or to flick sideways in order to get to the next page. Pretty straightforward. Another kind of modern mechanism is what's called an infinite scroll that you get with Facebook and Twitter, where it looks like you scroll down to the bottom, but then it adds a whole new page of material, right? So the scrolling keeps going on and on. It made a lot of sense for Twitter and Facebook that really did have kind of an infinite amount of stuff, most of which you didn't care about, but it has been applied inappropriately to lots of other mechanisms and lots of other web pages. And there's a recent article that talks about how bad of an idea that is for any content that's, not like for fun. And the new design for the HCI web page, if you go and look at that, which is on this hidden server, so it's not public yet, they tried to use this kind of infinite scroll for the people in the HCI Institute, and it was just a really stupid idea because, for one thing, Google doesn't index anything past the first page, right? Because when they're doing their scans, they're not going to, pretend to tap at the bottom of the page and go to the next page. So that would mean that only the faculty whose names begin with A through, C are indexed into the, and only the students, who are, in the top part of the alphabet would be indexed into Google, which makes no sense. And also, if you search in page, like Control F find, then you can't find stuff that's beyond the first page. Do you have another thought?
There was a website that has links on the footer, but also has infinite scroll.
Okay.
So you have to scroll down and then click on the link before it's loaded to this stuff.
Right.
Before the links disappear.
Right. You kind of have to go around it in order to try and convince it that you don't want it to scroll for you. Right. So there's lots of usability problems with this infinite scroll technique. So I don't recommend you use that in any of your pages unless it's, for fun content. And then another kind of variant is to put marks in the scroll bar, which is really useful for search results. It's used a lot in code editors to show you where the errors are in the code. So there's been a variety of ways to annotate this. And here's one from, I think it's Visual Studio, where they've really gone overboard with putting marks into the scroll bar. And so the bookmarks and the find positions and the caret, errors, breakpoints, all sorts of indicators are piled up into the scroll bar. So that's kind of the end of the scrolling mechanisms that I could think of. And I'm also interested to see if anybody else can think of any kind that we haven't covered. Yeah?
Sublime text actually shows a miniaturized version of the document in the scroll bar, which would be really handy if you remember what the shape of the text is.
Yeah, that's a good point. You could, if you have a slightly wider version, you can have a representation of the whole document. So also for pictures and things, it's like you can scroll down and see what the pictures are. So yeah, that's a good point. Any other ideas of different kinds of scrolling mechanisms? So in your homework, you're supposed to, yeah? Oh, okay. Okay, yeah, so going backwards and forwards. Anyway, in the homework, right, you're supposed to evaluate different kinds of scrolling in a web browser. And we couldn't think of any way of doing any of these kinds of things, like the hand or a dial or anything like that, because you can't use Acrobat to, go through the web or anything. So if you can think of any other cool ways of scrolling that you might be able to evaluate in your homework, that would be fine. But there are certainly plenty of other ones that you can use on standard devices. Okay, so the lecture is also to some extent about sliders. It turns out there's virtually no research on sliders. They're all pretty straightforward. There's one interesting thing was called alpha sliders, where I guess that's on the next page. Yeah. So mostly, almost all widget sets have a collection of sliders with different looks to let you pick some number in a range. Sometimes they look just like scroll bars, and sometimes they look slightly different. They might have incrementers on the ends, like conventional scroll bars. They go by one or some increment, and they may not. So the behavior is usually just like scroll bars, but it may be vary a little bit. These are some examples. This is the brightness knob from the iPhone, just a conventional slider. A slight variation is what's called range sliders, that you can pick a range of values in between, so it has two markers instead of one marker. And so this is from Kayak, where you can say, this is the whole range of time, and you're only interested in times between these two sliders, so you can pull them both in from the outside. Trying to figure out my Kai flights. Okay, So a few research systems. This is going all the way back to 1978. We mentioned this, I think, in the second lecture. The Spatial Data Management System from the MIT Architecture Machine Group was one of the first systems to have this overview. It's kind of like we were talking about where you can see the whole document in the scroll bar, but this is obviously a two-dimensional map. And so basically all the pictures on this are really little. You can't really see anything, but you can use, I think in this case, scroll joysticks to move around and pick which section of this is actually on the big screen. And so you're using this little map as a scroll mechanism. It's a fairly common way of providing this world view when you have a great big space these days. So pretty standard technique nowadays. I had two papers that I put into your homework as kind of reference material, and these both came out of my work with my advisor, Bill Buxton. He's really interested in two-handed use of computers. So you use two hands on the keyboard. When you're typing, you can sometimes use shift keys with your left hand while you're using a mouse with the right hand, but mostly your non-dominant hand is pretty much not being used while you're using the mouse with your right hand. So his idea was that we should put something interesting in your left hand, and so this is kind of a mouse replacement, and in the left hand was a slider, a physical slider, where you could use that to scroll. So our first experiment, we tried two-handed interactions. In the second experiment, we tried two-handed scrolling. And so you can see this X thing that we're using in the homework is way back from this experiment in '86. And what this box did is that this one was absolute. So if I hit my finger at the top, it would go to the top of the bottom. If I hit the bottom, it would go to the bottom. And this one is incremental, so it works like a mouse or like a scroll wheel that you could slide up and down. And so here it says select line 28 left, and I was supposed to scroll with one hand while clicking with the other. And you can see that the two-handed method turned out to be a lot faster than doing it with one hand with a conventional mouse. And one of the reasons it goes back and forth, of course, is when you're using a conventional scroll bar, you might imagine that things on the right would be faster because you can scroll and click, whereas moving over here would be slower. So that's something else you can look at as you're evaluating the homework and see if it seems like the ones on the right are faster than the ones on the left or whatever. When people were trying to click and resize, they did tend to use their two hands together. For scrolling, not so much. So we were checking whether people were moving the mouse like from the right to the left at the same time they'd be scrolling with their other hands. And we didn't see too much movement in parallel, but they still were faster, probably because they didn't have to waste time moving back and forth. Another interesting research system, this goes back to '93, and this was the idea that you can use your handheld device to scroll across where it seems like the picture you're looking at is like glued to the wall. And so it's like you're having a magnifying glass on it or a window onto the movement. And so the picture moves as you move your hand, okay? And nowadays you can do that with a smartphone with what's called optical flow. So you turn on the back camera and it can detect as you're moving and then move the picture that you're looking at on the screen. You could also theoretically do it with some sort of locating device like the accelerometer. So it measures your movement, and then the picture moves as you're moving the device. So it's kind of cute. It's kind of hard to see the picture as it's moving, right? So, and it's a little tedious. If you're trying to find something in a document, you probably wouldn't want to be doing like this. But it's kind of a fun thing to do, and it's probably okay for maps or something really large. And you zoom, kind of like you'd expect by actually moving in and out. Same kind of thing where you can basically physically try and control the scrolling. This is one of the very few research systems that tried to improve the scroll bar itself. And the idea of this system is that they took this indicator, the elevator, and divided it into multiple regions. And they were trying to figure out if they could help people scroll through really, really large document sets. So in this case, 10,000 items. So that's pretty hard to get to the individual items with a standard scroll bar because there just aren't enough pixels on the screen. And a basic scroll bar is limited, where's my cursor, to pretty much the number of pixels between one end and the other, which will typically be about 100, maybe 200 pixels at most. I guess if you have a vertical one, it could be 1,000 pixels. But you can't get to 10,000 items with only 1,000 pixels. It's just not possible to get to enough resolution. So the idea of this is if they tried a variety of different techniques. The simplest one was if you click at the top of the indicator, then it moved very slowly. So as you move the mouse quickly, the scroll bar moves slowly. If you click in the middle, it kind of follows the mouse. And if you click at the bottom, it went really fast. Nope, it's the other way around. Course was at the top and fine was at the bottom. And so the idea was that you could, pick in advance whether you wanted to go through the document quickly or slowly. Another one tried to use speed. So if you wanted to go fast, you would move quickly. And if you wanted to go slow, you'd move slowly. And it would then move the indicator in a relative amount based on how fast you worked. And another one pretended like you had a long, bendy spring attached to the thumb. So if you were right near it, it would be stiff and you could move it exactly. But if you moved farther up, it would kind of bend, and so the indicator would move much more slowly. And so by moving the mouse up and down away from the scroller, you could control the speed at which it moves across. So they tried those 3 different techniques. And for experts, the position one, the top one, seemed to be the fastest. So this is seconds, so you always want seconds to be smaller. For their experimental system, that also was true. And then this is a conventional scroll bar without any techniques. And the acceleration one, they all tended to be pretty much similar. And for non-experts, the middle two, the bottom two, this one and this one, turned out to be pretty slow and hard to control, much worse than a conventional scroll bar. So that wasn't a particularly successful experiment. So sometimes you try and invent these things and you think they're going to help people and it turns out not to help very much, which is one of the reasons that a lot of these techniques aren't in general use. The problem with rate-controlled scrolling is, hopefully you'll find this out in your experiment, is there tends to be a lot of overshoots, right? You know where you want to go, and if you see it, and it's, whoops, there it went, and you see it go past, and then you have to backtrack, and that's always much slower.
I have a question about this for
Yeah.
Like I think it reminds me. I think the iPhone has the micrometer implementation, like in scrubbing like a song or a video. Like if you when you're scrubbing, if you move down, it'll lower the speed at which you move through the video. So it's interesting that this paper showed that it tends to not work very well yet.
Well, the other thing about that is I didn't even know that, right? So there's no affordance that would show that that's there. So that's another issue with a lot of these interaction techniques is, do people even know about it, right? So if you had a little marker on the thumb like this one, it kind of says, oh, there's something interesting about this that maybe you'd want to investigate. But this technique about moving at a vertical distance, you'd never know that was available. So that's a good thing to try. I really want that on YouTube videos because I'm always trying to move slower. Yeah.
What would some of YouTube implemented for sliders when they're really long videos? Like once you slide to the spot, another slider comes on top so you can get even more precise where you are. I haven't seen it since, so I don't know if maybe they would make bad.
Anybody else see that on YouTube? That a multi-level scroll bar? Okay. Yeah, that's interesting. I certainly, like when I'm trying to do all the widgets video, I keep having to try and go back a few seconds, and it's always a real pain. So everyone always thinks, oh, now we have tilt sensors in these things. Wouldn't it be a good idea to use tilt as a way of scrolling? Because you can kind of imagine your document falling off the end, right? So then it would, you tilt it this way, it would scroll down. And so sure enough, people have done that. There's a 96 system from Jun Rekamoto at Sony, who's done all sorts of really interesting innovations with handhelds. And so he did that both with menus. So he had kind of this wheel look, which predates the Macintosh by at least a decade. But it kind of looks like what we see now on the Macintosh, on the iPhone, where it looks like a wheel, and you tilt it, and it would go in one direction, and you tilt it back, and it would go in the other one. And he also did it for maps, where you could tilt it and scroll around the map. But turns out this is not very popular, and Ken Hinckley re-implemented this in 2000 on more modern hardware. Did some user tests with it. One of the big issues, of course, is when you tilt the screen, you can't see it anymore, right? Because it's no longer, you can't look at it exactly. So if you're holding it like this, if you're holding it right side up, then the text should go down, right? Because you're tilting it down. And then, so you also have the problem that how do you tell it when you want it to scroll? And if you have to do some gesture, then maybe that should be what causes it to scroll anyway. Why do you need this tilting mechanism? And it's really hard to control. It's really hard to see when you get there, because if you're tilting it down like this, so it'll go that way, you can't see the screen anymore. And especially with LCD screens, if you're a little off angle, then they get much harder to read. And so Hinckley, in his experiment, tried to increase the brightness of the screen if you tilted it away from you, just to compensate. But that was really kind of silly, and it didn't really work. Yeah?
So my phone, the PS4, it has like the eye tracking, so when you look up, you can scroll, and I thought, would that be better if, with the technology developed, would that be something that would get through?
So there has been work on eye tracking as a scrolling mechanism. So this dates back to, well, this was from 2013, so it's fairly new. And there's the one on your phone. So do you leave it on, or do you turn it off? Yeah. Yeah, my son had that too, and he turned his off too. So as far as I know, for almost all eye tracking mechanisms, there's what's called the Midas problem, right? So there's the story of Midas. Everything he touched turned to gold, and he accidentally turned his daughter to gold or something like that, because the problem with this power is the things you do naturally are causing unintended consequences. And the same thing's true with gaze tracking. You're always looking at something, right? And sometimes you want, just to look at things. And the problem with eye tracking is that it can't really tell when you're trying to look at it in a way to cause something to happen versus just looking at it because you want to look at it. And so almost all eye trackers have this problem that they start doing things when you don't want them to, and then you have a hard time getting them to stop. And if you had to do some gesture to tell the gaze tracker to do something, well, you might as well have the gesture do whatever it is you want to do, like scroll or whatever. So that's a general problem with scrolling. This paper had that problem as well. They didn't even do an experiment, and they just asked people if they thought it was a good idea, and how they were trying to measure how big a reading area was, so that they could tell if you looked out of that area what should trigger the automatic scrolling. But in general, eye trackers have only been particularly useful for people who are handicapped, who really can't have other mechanisms of controlling things, and who are willing to stare at something for a few seconds in order to trigger things to happen. But for the general public, it's really turned out to be not particularly interesting. And one more paper I wanted to present. This kind of goes back to the original one I was mentioning, where we were looking at two hands. So in the late 90s, early 2000s, I had a project on Palm Pilots. And so we did an experiment where we took some of those controllers that previously we had to build special hardware for and just put them on a Palm Pilot. And so the idea was that you would take your Palm Pilot and put it in its cradle on the left of your keyboard, and you'd have your mouse on the right of the keyboard, assuming you're right-handed. And then we drew onto the Palm screen some buttons or a slider or a rate-controlled joystick. And the idea was to see if we could reproduce the same behavior that we saw 10 years before, where you could use it much more efficiently to do scrolling. And the results were pretty similar. The mouse was a little bit slower than the button scroller, which is this one. And the rate scroller, which was really bad, because again, everybody was overshooting, and we iterated a whole bunch of times on the transfer functions and trying to make that work out well. Not very successfully. It was pretty slow and error prone. The absolute scroller was pretty good, where you said this is the top, this is the middle, this is the bottom. And so wherever you jump to, but obviously with your finger you don't have very much resolution. And in this one we use the big document that's being used in the first part of the homework. Okay, so the homework takes the 10 pages from this study and the 10 pages from the other study and combines them together. Okay. Any thoughts or questions about scrolling? Okay. So today's topic is models. And since most of you guys aren't computer scientists or don't really care about mathematical formulas and stuff, and next time we're going to talk about text entry, which is much more important and interesting. I'm not necessarily going to finish all the slides that are in this deck, and if you're interested in some of the other material, you can certainly go on it on your own. But in general, mostly we're just kind of thinking of problems and trying to fix them when we're creating interaction techniques, thinking of a control we need and trying to figure out a way to do it. But maybe we could do a more conscientious, more thorough job if we had some sort of understanding of the space of all possible techniques or all possible mechanisms. And so the idea of a model, there are a variety of goals for it, but one is to kind of give you an understanding of the space of all possibilities. What sort of things could you do? Where have people tried? Maybe that'll show you some things that people haven't tried, and you could try something there. Another use for models is to try to give you a more precise description of what's going on. So maybe there's some parts of the interface that are undefined, and this would help you understand that. And then finally, some of these models are techniques to help you evaluate the speed of things or the other aspects of the performance, errors and that kind of thing. And so it might be nice to be able to not have to do a user test like we're doing in the homeworks, but actually just calculate how fast something's going to be. And so that's what the keystroke and GOMS models are for. So the first one I want to go over are transition diagrams. How many people know what these are? I would guess all the computer scientists and nobody else. So about a third of you, that's kind of what I expected. A transition diagram is a formal way of talking about the modes or states of the system and what causes you to change between states. So a fairly simple example, I have this box here, and here's the mouse, and sometimes the mouse can move over the box, and that's called hover. Okay, I haven't pressed any buttons, I just moved the mouse over. And so I have two states, the start state where there's nothing much of interest going on, and then I move the mouse over the box, and that gets me to the hover state. Okay, there's two states, and you can imagine that maybe you'll want to change the color. Right, that's a pretty common thing to happen. If this is an active widget, and I move my mouse over it, it should change color. Or maybe the cursor will change picture. Right, if I can click on this, then this might change to a little hand or something like that. That's what happens on the web all the time. Or maybe the underline will appear. All sorts of graphics might happen. So I want to know, if I go mouse over, I get into the hover state. And how do I get out of the hover state? It's pretty straightforward. I move the mouse away. So that's this fairly simple part of the state machine. So these are called states. These are called transitions or arrows, pretty straightforward. Okay? So when you're in the hover state, then what might happen? Well, then you might push the mouse button down. And so that's this one, mouse button pressed down. And then we'll call this the selected state. You could call it mouse down state or something. And how do you get out of the selected state? Well, you release the mouse button. It's pretty straightforward. And here, maybe you'll get some different feedback, or it'll give you an event or cause something to happen. So this would cause some behavior. So is this a complete diagram of everything that can happen with respect to the mouse and that box? Does anybody see any things that are missing?
You can release the mouse, but it doesn't, and move it away, so it's not happening anymore.
Well, if I release the mouse button and then move it away, then I can. Then that's still in the diagram. Yeah.
Mine can more than one button.
Okay. We're not going to worry about the other buttons. Okay. So certainly there's all sorts of things you could do. The other parts of the, there's all these keys. You could hold down the shift key. You could type a Z or an escape. So we're going to assume, and that's one of the things that we'll talk about later, that everything that's not on the diagram is not relevant. But there is something relevant that we haven't captured. Yeah?
You can mouse away while the button is pressed down.
Right. So if I hold the mouse down and move away, what happens? Okay, so according to this diagram, that's not possible. But of course it is possible. And so you really need to have another state which is pressed but outside. Right? So if I'm inside this box and I press the mouse button down, and while I'm pressing it down, I pull outside, then that is none of the states that we previously had. It's not hover, because I'm not over it, and it's certainly not back to the start, because we have the mouse button down. So we need a brand new state to deal with that, called pressed but outside. I mean, you could come up with your own name for it. Okay, is that everything?
We need to transition back to the start if we let go.
Okay, yeah, so if you let go from here, then what happens? Well, what's supposed to typically happen if you let go while you're outside? Right, it aborts and goes back to the start, right? So we need that one too. So is this a complete diagram? Yeah?
No, because if your mouse is down, you can move it to select something. You release this, go out to start.
If you move it back in?
No, you move it, so you press it down, not over something.
Press it down outside?
So, yeah, press it down outside and drag. You select the object, like, in a different point.
Okay, so that's another way of selecting things. If you happen to be supporting region select, okay, if this was a radio button, then that wouldn't be part of this behavior. Yeah?
I think actually related to that, but not exactly the same. If you press down outside and then move over the object and then let go, not hover is, I guess there's a question of.
Right, so it depends on what kind of thing we're talking about. If we're going to talk about like one of these widgets, let's select something. Now we've got all these widgets here. So there's a hover, a press. Notice it changed color. If I pull outside, it goes off. But if I press outside and move in, it ignores that. Right, so this particular widget doesn't have any particular behaviors other than the ones that are in here. But the other thing that I just gave away that we wanted to talk about is when you actually do the action. And it's only on this transition. Right? If this is like turn bold button or something like that, the action of actually causing whatever this button said or becoming selected or whatever only happens at the point where the mouse button is released. And everything else just deals with local feedback. Right? And I guess an interesting question is, do you still get the hover feedback? If I press and release, yeah, it still has the hover feedback. So this is kind of modeling the radio buttons or these kinds of behaviors. Other things like if I click on here and move, then I'm going to get this thing doesn't have that kind of behavior going on. Okay, so this is called, come on, wake up. I need a spinny thing. Okay. There we go. So this is called a transition diagram, and it's really useful to make sure that you've got all of the behaviors in your interaction technique covered, all of the different possibilities. And many people who implement their own interaction techniques, like you'll see these on Flash implemented scroll bars and Flash menus and stuff all the time, is they forget about like this section. And you can start scrolling, move your mouse out down and release, and it's all confused. Right? It thinks the mouse button is still down even though it's not, or it continues to scroll when you don't want it to, or selecting things randomly. So it's very useful to remember how to do this kind of model if you're inventing your own scroll bar, or if you want to make sure you've covered all the different situations. It turns out that these transition diagrams are a very old way of describing computation, and it predates computers even. People who were mathematicians were using these kind of diagrams to think about logic. And so it wasn't very surprising that when the computers came along, people used these kind of diagrams to describe computation. And way back in 1968, William Newman, who eventually went on to be big in graphics, used transition diagrams as a way of describing a user interface. It was probably the first tool that lets you describe user interfaces not by writing code. Right? So he would let you describe these diagrams, not so much in graphics. They didn't have graphics terminals in '68, as you can imagine. So you would describe it kind of textually. It would generate these diagrams for you, and it would generate the code to do the user interface, probably in Fortran or something. So very ahead of its time kind of system. And you might think, oh, why aren't we using this all the time? It turns out it makes a lot of sense for fairly low-level things like interaction techniques, which is one of the reasons it's important for this class. But for most user interfaces, they're really totally inadequate and not appropriate. And so there's this great book by Dan Olson where he tries to say, well, let's generalize the idea of transition diagrams and make it useful for regular user interfaces. And so he gives it a start. This is the idea of a template palette where you're trying to pick what you can draw. So you could draw a line or you could draw a rectangle, and you can imagine in a real one you'd now have 15 or 20 different whole diagrams that would have to come out. So you're drawing a line, and if you do a mouse down, then you're drawing the other end of the line, and then when you're finished, then you actually do the drawing of the line. If you're drawing a rectangle, you get 1 point, and then you get the other point, and then you can draw the actual actual rectangle. And so you can imagine you could start down that path. One of the problems with these is that if you think about how you would represent those in code, it turns into some kind of text like this, which is basically full of go-tos, because each of these lines is a go-to. And so in regular code, it turns out to be really impossible to understand, and it tends to be hard to debug and stuff. But more importantly, there are all sorts of things you'd want that are hard to express. So like, this is a procedure call, and it's really hard to figure out how you would map a procedure call into this kind of mechanism, because every line has to have some kind of event that happens on it. So I say I want a circle by clicking on the circle icon, and then I want to type an integer, but the first type of an integer, like if I type a 1, that has to be consumed by this line, but I really want it to be consumed by this line so that I can accumulate the value that I'm typing. And so somehow you have to figure out that there's this procedure call, but what causes it to start is the same thing that has to be mapped to part of the procedure call itself. So it really doesn't work very well as a way of having what are called subdialogues or procedural abstraction or anything like that. Another thing is that suppose you want something like escape to abort all the time, or command dot, or something like that. So you remember these diagrams we had before. If you wanted to say at any point I can always hit the escape key and quit, right? The general assumption like we were saying before, is that anything that you don't show on the diagram does nothing. It's just a no-op. And suppose you wanted it to do something particular. Well, then you'd have to have an escape line out of every single state, which is pretty, tedious and awkward. And so the idea in the book was, we'll just have this meta state down here, which says anytime you hit the escape, then you go back to start. But this is kind of weird because it's not connected to any of these boxes. And the whole point of state transition diagrams is you can tell at every point everything that can happen by just looking at it. So, if you're showing this to somebody and you say, this is everything that can happen, and the programmer says, well, now I know exactly how to implement this behavior because I can see everything that can happen. And now you want to say, and by the way, from every single state, pretend that there's another line called escape that will take you back to the beginning and clean up anything that's, any of the feedback and things like that. So that's another kind of mechanism that's a little weird. And then you get into wanting to do more sophisticated stuff that you can't actually express this way. And then it turns into something called augmented transition diagrams, where you can actually have code on these lines instead of input events. So far we've said mouse down, mouse up, pretty straightforward kind of things. But in some interactions you want to say, is the object over a legal place? Or did the password they typed valid? Or something like that. And so you need to do some computation to figure out whether things are valid or not. And that is called an augmented transition network. So the idea of transition diagrams are pretty useful when you have something simple because everything is right there in front of you. You can see what's happening. You can see the order things happen in. It's pretty clear at any point what happens next and what happened before it. So you've got a nice ordering. It's most people can understand it. If you showed it to a random person and said, you are here, where can you go next? They would be able to tell you. So it's not really very complicated. And so it seems to be really useful for some of these kind of low-level behaviors that are very much structured, and a lot of widgets are like that too. On the other hand, there are all sorts of problems. One is it doesn't scale at all. This is an example with just 3 different possibilities, A, B, and C, but the user is allowed to type them in any order or enter them in any order. So you can imagine I'm picking a color, I'm picking a line style, and I'm picking, line width. And I have those 3 parameters. I can pick them in any order. It would be really hard to express that in a transition diagram because you have to have every possible order presented, and so you end up with a stupid diagram like this, which really makes no sense at all. Right? I can pick A first, or I can pick B first, or I can pick C first, and if I pick B first, then I can pick A or C, and then finally I can pick the other one. Right? And so you end up with silly diagrams like this that make no sense. So it really has no validity, or it doesn't help at all for things where you can pick things in any order. And so, all the parts of a graphical interface that allow free choice don't work very well. And it also doesn't mention really much about what happens with the input that's not specified. Generally, you assume it's ignored, but maybe you want to provide some kind of error message or something like that. And there's nothing about the output or what happens. Remember, when we looked back at the original one, it doesn't say anything about what happens to this box. What's it look like? What is the actual action that happens as a result of here? And so sometimes you'll try and put some kind of annotation on each of these or in the states to say, oh, when this happens, then it turns darker, then it turns outlined or whatever. Yeah? Flowcharts? Are you thinking of flowcharts? Yeah. Yeah. So. Yeah. So there are lots of different kinds of diagrams. She's talking about flowcharts, which is a fairly straightforward representation of the sequence of actions that happens. It would look entirely different than this if you tried to represent this in a flowchart. In a flowchart, so there's choices here, right? So from hover state, there's two things that can happen. I can either push the mouse down or I can move away. So there's two outputs here, and that's a choice. In a flowchart, every choice has an explicit icon, which is usually a diamond. And so you'd say, the user has to make a choice. Does he do this or does he do that? And in state transition diagrams, they're a little better for user interface kind of things because the choices are implicit. They're not actually, you don't actually have to say each choice in the diagram. It's just, you understand there's a choice because there's two output arrows. So that's another thing. And flowcharts are very explicit about loops. So let's do this over and over again, or let's do this 5 times. And loops in this kind of diagram are always implicit by just going back to the beginning, right? So, this thing is going to wait forever, and if I go in and out and in and out and in and out, I don't have to tell it how many times I'm going to do that. I can just do that an arbitrary amount of times. So there are lots of different representations, and some have advantages and disadvantages compared to others for different kinds of things that you might want to represent. And generally, state transition diagrams have the one that's been mostly used for user interface kind of things because of this event-based kind of thing. So you have a line for each event or each thing that's going to happen that causes it to change states. So it seems a little more effective than some of the other diagrams like flowcharts. And there are other ones like data flow diagrams that maybe you'll come across. There are all sorts of them that programmers, mathematicians have invented that, in my opinion, are less clear than these, or even less clear. It's one called Petri nets that the Europeans really like, that sometimes you see as like supposedly helpful, but I find them unusually difficult to understand. Okay. So that's really the only diagramming thing that we're going to talk about. And as you get to the part of the course where you're designing your own interaction techniques, or if you're thinking about another thing that's very similar to transition diagrams is actually site maps. So if you're building a big website and you might draw a map to show where, and then in that case, each page kind of represents a mode or a state. And then the transitions between pages that are allowed would be the kind of diagram that you might draw as your site map. And of course, it's not considered to be like everything that can happen, because in real websites, of course, you can jump anywhere using search, and there may be an index where you could jump to every page. So that's not kind of useful, but you can kind of get a general overview of the standard ways people navigate around sites. Okay, so jumping back to other models. We've mentioned Foley and Wallace before. They're very important early thinkers about user interfaces. So this dates back to '74, where you can imagine that the way people interacted with computers was quite different than it is today. So they were trying to think about what are the basic ways that we can interact with graphics. And they came up with these 4 different, what they consider to be fundamental devices or interactions. Pick was identifying user-created objects. So that's like picking rectangles that you drew on the screen or picking icons. A button, they listed for all system-defined items. So this was menus, buttons, clicking on anything that the program was providing for you. Locator was giving data like the position of something. So that would be like if you're going to say where this rectangle goes, or if you're going to pick a point in text, that would be a locator. They also use that for multiple points. So the size of a rectangle, it would be from here to there. That would be 2 locator inputs. Or an orientation, you could say, from here, rotated like this. So that would be a locator as well. And then they had evaluator, which was like the output of a scroll bar or a slider, but it also could be a knob. So back in the early days, they had knobs, as we talked about last time, to any kind of real number value or percent or whatever. The same paper also divided up the inputs into different levels, and so we'll talk about that next. So what do we mean by levels? So Buxton wrote a paper where he took the levels of Foley and Wallace and added some more. So we're going to talk about the 5 levels, which are the 3 levels from Foley plus the 2 extra ones that Buxton added. So the first one, according to Buxton, is the pragmatic level. So this is kind of how the interaction device feels. So how does the mouse work? Well, there's a physical button that goes click when you press on it, and you can hear the click, and you can feel it with your finger, and you can move it physically around the table. And so that's, you can kind of feel how it scratches around the table, and it makes a little noise. Okay, so these are all parts of the pragmatic level of the device. And you might imagine that some buttons are harder to press than others. If you're trying to use the pointing stick with a physical button on a Lenovo or a ThinkPad computer, then you have to use 2 fingers, and one's on this knob and the other one's on the switch. So it's kind of the orientation of your hands, what the actual gesture is, how hard it is to press. If you think about, how do you use the mouse, you'll probably realize you don't think about it, right? You think about, I want to click here, and you, at this point, are so expert at using the mouse that you never have to think about it anymore. And, however, if you've ever looked at a little kid or a grandmother trying to use it for the first time, it's actually really tricky to use a mouse in an effective way. And you heard David Smith talk about back in the 70s and early 80s when they were trying to introduce the mouse to people, they were all confused about how it worked. And so there's something called muscle memory, and anybody who's an athlete or, highly trained in any kind of activity knows that, at first you have to think very carefully about how your muscles are going to move, how you're going to do some activity, if you do yoga or if you play basketball or any kind of physical activity, you have to practice, and eventually you get so you don't have to think about it anymore. It's called muscle memory. And you just kind of have this practice behavior. The same is true of input devices. So how many people here are touch typists? Okay. How many people here type with 2 fingers? Okay, what do the rest of you do? Just don't answer questions, right? 1 finger on a keyboard? So if you're a skilled typist, then you learn to type without thinking about it, right? And that's kind of the ultimate goal of becoming a touch typist, is that you can type fast, pretty much as fast as you can think, and so you don't have to be concentrating on your fingers anymore. So the whole idea of muscle memory is at this pragmatic level of, can you learn to use this device without having to think about it? And how efficient is it to use basically without any cognitive intervention? And it also includes things like whether you press down and hold or whether you go click, click. So it's all about kind of the really low-level physical parts of the interaction. So the next level is called the lexical level, and this is the notion of tokens, or how the actual item is spelled, or what the actual item looks like that you're interacting with. So this is a level where you would differentiate whether the word is add, append, or whether you use Control A on the keyboard or use an icon, right? So you may have a whole bunch of different ways of invoking the same basic operation. And certainly that's true in all menu systems. So if I want to cut something, I have 3 or 4 different options for how to cut. And that differs at the lexical level, right? So whether I go to this menu and press it, it also includes where they are physically on the display. So if you're wondering how long will it take me to get to this menu item, that's basically a lexical question according to this differentiating. It also is where you would do the keystroke level analysis. You know, how long will it take a person, if they're really fast, to do this operation? And so, you know, how fast can you type Control-C? You know, it's not instantaneous. It takes a certain amount of time. If your fingers are on the control, on the home position, you have to move your little finger to the control and your other finger to the C, right? So how long would that take? But still, no matter what, it's going to be a lot faster than moving up to the menu, clicking down, pulling down to copy, and then releasing, things like that. So in the interaction techniques that we're designing for this class, you know, there's a lot about the interaction at the lexical level. How fast can you scroll? How fast can you type? How fast can you click buttons? Things like that. The original Foley paper talked about when you do some operation, what sort of feedback do you need to see? And how fast does that have to be produced? Nowadays, we really don't worry about how fast things are. But in 1974, that was a really big issue. And you can imagine that if you, and still this happens on badly designed programs, that you do some operation and you get no feedback at all, and you have no idea whether it's listening or not. So the lexical feedback has to appear right away, within 50 milliseconds, or people think they weren't heard. Right? So if you click on a button and it doesn't actually show anything, within 50 milliseconds, you're likely to click again, thinking that it hasn't heard you. Right? And so often, the modern operating systems will go into some bizarre swapping mode or sleep mode and not answer you for a while, and then you get, you know, suddenly it'll wake up and answer a million times. So this is the lexical level feedback has to be provided fairly quickly. The next level is syntactic level, and we've talked about this a bunch of times in terms of the syntax or the order of operations. And we talked a bunch of times about prefix and postfix and infix. Remember, we had a lot about that. That's the syntactic level, right? So if we're talking about, we were talking about graphics. How do you, copy and paste things? You select, copy, move somewhere, paste, or select, drag, and drop, right? And the fact that we said copy, we didn't care how you invoke the copy operation, whether you used a menu, whether you use the icon, or whether you type Control-C. The copy operation still always has to come after the selecting of text or selecting of the graphics. So the syntactic level that talks about what order your operations are pretty much independent of the individual tokens that describe how you do each of the low-level pieces. So this is the sentence level, and if there's any feedback, this one can be a lot slower, right? So if I do a copy and paste, and it doesn't, and I don't see the results of the paste for half a second, I'm probably going to be okay with that. I'm not going to be all panicked that the system is not waiting or not responding. So up as low as 2 seconds in 1974. Today we expect things to be a little faster, but it's not like the hover feedback or the click feedback that needs to happen instantaneously. The results of these operations can be shown a little slower. And then finally, there's the semantic level, and this is typically where interaction techniques stop. That, after I click on a button, then something's going to happen in the application, like something will turn bold, or something will be deleted, or some new text will appear, or whatever your button is supposed to do. That's the semantic level. It's kind of the behavior that your interaction technique involves. And so it's the functionality of the system. It's kind of the callback or whatever in the real code. It also includes whatever kind of errors can occur. So I try and do a paste and it says you can't paste here, or I try and save the file and it says there's a disk error or whatever. So whatever kind of operations, it goes back to the application and says application, the user has finished their interaction, they're ready for you to do something, then the application has to figure out how to do it. And there's going to be feedback typically from the application about what it's doing, and typically it's considered okay if that takes a little while for the system to come back. So you can have feedback in a few seconds, up to 10 seconds or so, and nobody's going to be too worried about the system crashing if it comes back eventually. So we've got those levels, and then Foley and Van Dam in their textbook added yet another level, which is more about kind of the user model or metaphor that the system is trying to present. And this, again, really has nothing to do with interaction techniques, so we won't talk about it very much. But it's the basic idea that there are kind of higher level concepts that go beyond just what the individual operations do. So you might want to describe what are the different kinds of objects in the system, and what are the behaviors that you're allowed to do on those objects. So in a text editor, the objects are characters, files, and paragraphs. In a code editor, they may also add things like expressions or methods or objects. What are the relationships among those objects? So files contain paragraphs, paragraphs contain characters, the operations, insert, delete, things like that. So it's kind of the model, the user model, the metaphor. What are the basic units in the system? Foley calls that the conceptual level. And as user interface designers, you're going to have to deal with all 5 of these levels. If you're just designing interaction techniques, then you're mainly focused on the lower level ones. Okay. A totally separate model came out of the community of people who are trying to help with implementing user interfaces. And I just like this one because it's so silly. So this was invented by a group of people who met in Seeheim, Germany, way back in '83, and so they call it the Seeheim model. And the basic idea of this, and the reason it's important, is that you've got your application over here, and there's this separation between output and input. Okay, so remember when we were talking about transition diagrams, you were saying, okay, the mouse goes down, the mouse goes up, the user moves in and out. It's all about the input. It's all about what the user does with the input device. And that was in this box. And they still, just like transition diagrams, decided to separate out the behavior results, the feedback, the graphics, into this other box. And there was some sort of bizarre arrow that's going to somehow communicate between these two or connect them together somehow. And then there was this blank box down here, which they never described, which turned out to be where kind of most of the interesting behavior happened. So this model had a lot of influence on the way people were thinking about things, but it never was really implemented in practice because all of this ambiguity about what these boxes really meant and what this empty box was and what the arrows were. But this general idea of separating out the input or the dialogue from the presentation turned out to be a very important and long-lasting part of most of these models. And if you think about the interaction techniques that we've looked at, scroll bars, buttons, text editing, graphical editing, these two are tightly linked. Right? You can't really imagine describing a scroll bar without talking about both what it looks like and what you can click, where you click and what it does. Right? So you can certainly say, and it doesn't make any sense to say, well, you click in the trough without saying, and the trough, by the way, is this area above the indicator, and that's all about the tight interaction between the graphics and the behaviors. So scrolling with 2 fingers on the touchpad has no presentation at all, so that's kind of handy. That would fit very nicely into this model because it would be all in this dialog box. But most of the interactions we've talked to have a fairly tight coupling between the behavior and the presentation. So in the area of interaction devices, notice this is '83, so this is right as the mouse was becoming well known, but before it was ubiquitous. So nowadays, everybody knows what a mouse is, and pretty much all interactions are either mouse or fingers, maybe styluses a little bit. So we were wondering at this time, what are some of the dimensions that we could have with input devices? And you could still get physical input devices like the knobs from Sketchpad, rotary knobs. You could still get some of these and plug them into your computer and use them for things. I guess you can still get them in terms of game controllers. You can get a steering wheel, for your game system, and that's kind of a rotary thing. So some of these are still somewhat relevant. I guess you have the scroll wheel. That's a rotary thing that is a one-dimensional input. And so the idea of this tableau is to try and separate out some of the choices and show kind of where they're blanks, so that a rotary potentiometer is a one-dimensional thing that's rotary, and you could also have a sliding potentiometer, which is one-dimensional. For two-dimensional things, we have a mouse, which is motion sensitive. So mice are not position sensitive, they're motion sensitive, versus position sensitives, which are tablets of various kinds. The old light pen that we saw from Sketchpad is also a two-dimensional position-sensitive device. And an isometric joystick, which is the kind in this laptop, which is spring-loaded, is also position-sensitive. And then there are three-dimensional devices, which we haven't talked about yet, as well. So you can have 3D joysticks or 3D tracking and so forth. So not particularly interesting. It's pretty obvious that you can divide things up into these ways. It doesn't really help very much. But if you were trying to invent, you had some kind of 1D input or 2D input, and you were wondering, what are all the different ways I could let somebody pick a point in 2D space? Then you might go to some sort of diagram like this to say, what are all the choices for two-dimensional input? And then you could look and see what sort of device you might be able to take advantage of. So once somebody makes a model like that, then everybody thinks of things that don't fit into it. And sure enough, that happened with that model that Buxton presented. So this is, what year? 90. Stu Card, Jock McKinley, and George Robertson at Xerox PARC said, oh, Buxton's model is kind of interesting, but it's not nearly complete. We can think of all these other things that he forgot. And so they came up with this fairly formal model. They say the input is a 6-tuple, so people who like math would immediately think this is fun, where M is the manipulation operator and N is the input domain and so forth. So personally, I think that's a little silly to introduce math into this, but they've basically taken Buxton's model and added more choices. So one of the things that Buxton ignored was switches. So this one also tries to get into other kinds of inputs besides just the mouse and things like that. And so the Buxtons are the squares and the hexagons. And so you can see there's a variety of different choices here, but they also have menus and keyboard. And so the Data Glove is a 3D manipulating in space that was available. So this is kind of similar to the Buxton one, just a little more complicated because they added in more choices. So neither of those are particularly important in terms of their influence. They're just kind of interesting as a way of kind of understanding some of the different things that were available at the time. The model view controller idea, on the other hand, has had a really big impact on software, on design, and almost all of the programmers, if you do any user interface programming, you kind of have to be aware of this model view controller idea, which was invented about 1988 in Smalltalk by the Smalltalk guys over at Xerox PARC. And again, they were trying to separate out the different parts of the code. So there's the code that handles the view or the look, the presentation. There's the code that handles the input, which they call the controller. And then there's kind of what happens, the semantic part, which they call the model. So this is, not too different than the CHI model that we were talking about, where you've got the model, the view, and the controller. And so this is much earlier, 83. So people have been trying to figure out ways of separating out the code into different parts and making things replaceable. And the model view controller is one of the more famous versions of this. It sounds pretty straightforward, but it's kind of hard to do in practice, it turns out. And even this original paper, the Krasner and Pope paper, which is the famous paper that introduced it, it turns out to have been kind of published in an obscure place, and for many years was really hard to find. Now it's all over the web, of course, but at the time it was really hard to find, and there's this kind of bootleg copy at University of California at Irvine that everyone refers to that is the only way to find it anymore. So the basic idea is you separate out the code into these parts, and you could have one model, which is like a number, and you could have multiple views of that model. So here's the 345. It could be represented as a text field. It could be represented as a slider or a scroll bar or a potentiometer or thermometer or something. So these are all different representations of 345. And you can imagine that different ones of these would be useful depending on what you wanted to do with it. And the idea of the controller is how the user can then provide input or control the value. Pretty clear name. So the controller would be the thing that handled the input for this. But as you can imagine, you need to tightly couple the controller with the view. So whichever kind of controller is going to handle the mouse down is going to be totally different than the kind of controller that handles typing. And so most of the time you end up with the controller as tightly coupled with the view. So the model is the semantics, the representation of this behind the scenes. What is the actual value? So for a button, it might be a Boolean, whether it's true or false, or pushed or not pushed, on or off. For a number, a scroll bar, it's just a number, 12%, 345. So often for interaction techniques, the model is very simple. For a menu, it's a list of the items and whether they're selected or not. The view is everything graphical, including the layout. And then the controller is all the code that handles the behavior. So if you were doing a state transition diagram, the model would be, the model would be, whatever it is that the data is behind the scenes. The controller would be the state transition diagram, and then the view would be whatever you're going to have for graphics. So starting in 1990, or actually in 88, but I wrote about it in 1990, took this idea and actually implemented it in a couple of toolkits that I invented at the time. And I was able, because of some of the designs of the software, to actually provide behavior objects, 6 behavior objects that encapsulated pretty much all of the behaviors that you needed for graphical interfaces. So one was the choice behavior. We called them interactors. They're basically behaviors. So the choice behavior you could use for menus, but you could also use it for choosing items in a graphical editor. So anytime the user had to choose between multiple items. There was a moving and growing behavior, which you can imagine was for moving and growing. And we could use that for moving the indicator in a scroll bar, but also for dragging objects in a graphical editor. A new point interactor was kind of similar, but it was when you didn't have anything to move, right? You're just, going back to the old Foley thing, it's just providing points, typically 1 point or 2 points. Angles, pretty obvious, it's when you needed an angle. Text interactor was for typing. And then gesture interacting is when you wanted a freehand path, like a curvy path. And so that's unlike, if you wanted a new line, you'd say point here, point there, and it didn't matter how you got there. But if you're trying to circle something, or if you wanted a wiggly path, then you'd use a gesture interactor. So the idea of the interactor model was that we could take these behaviors and plop them on top of any arbitrary graphics. And it worked surprisingly well, and it's been pretty influential. And then the final thing I have a little bit on is human performance modeling, and hopefully all the Masters of HCI students in the room are really familiar with this, because I don't know if it's part of your curriculum, but it used to be. And the idea of human performance modeling is totally different than the stuff we've talked about before, but this is modeling what the person is doing, or the thinking of the person. So it doesn't have anything to do with how the programming works, or how many different input devices there are, but it's all about what the user's thinking and doing. And the idea is that if you could have a model of how people work, then you could just apply that model to the user interface, and you wouldn't have to do all this silly user testing that we do now in order to measure things and to see if things are usable and stuff. So their question is, can we determine the properties of usability, of performance, of errors, without actually doing an experiment? And the answer is surprisingly yes in many cases. So the kind of lowest level thing is how long will it take to enter the sequence of values, what errors will people make, and so forth. And so this is Mr. Bubblehead. That's what they called him. And this goes way back to the early 80s. Do I have a date? Yeah, I'll have to put the citation in here. So this is from a very famous paper and book. It's actually called Human-Computer Interaction. It's considered to be the origin of the name, HCI, the book that this comes out of. It's a white book that was done by Card, Moran, and Newell. Alan Newell is the guy this building is named after, was a very influential psychology professor here who was also in the computer science department. His former students, Stu Card and Tom Moran, had gone to Xerox PARC, but they continued to work together, and they came up with a lot of this psychology that is kind of the foundation of human-computer interaction. And Mr. Bubblehead here is a way of representing some very fundamental measures about human performance. And next Wednesday, Jeff in his lecture will be covering these in more detail, but it's basically psychologists have measured, given that you're thinking about pointing to something, how long will it take you to realize that that's what you want to do, send the signal from your head into your muscles, and how long will it take your arm to actually perform this operation? So there's minimum times that psychologists are very familiar with of, if I'm looking at something, how long before I can recognize it, and how long can I use to get there. So, and that's what kind of all these numbers are for. It lets you kind of sum all these up and say, well, if you're expecting the user to see something, recognize it, and click on it, there's a minimum amount of time that could possibly take, and you can just calculate that. And so that's what all these numbers are about. It also includes things like how much can you remember. So 7 plus or minus 3, you've probably heard that, 7 plus or minus 2, something like that. So there are all these kind of constants that psychology is measured. And there's something called the keystroke model, which is basically taking all of these low-level numbers and saying if we expect somebody to type 4 letters, move their hand to the mouse, and click a mouse button, we can just calculate the time that would take. And that assumes you don't have to think about it, right? So the keystroke level model pretty much assumes that it's what's called expert, like we were talking about before, muscle memory, right? You don't have to think about it, you're just going to go click on it. How fast could that conceivably go? So you don't have to measure that, you can actually calculate it. And it gives you a prediction of this time, and they've shown that this can be accurate within 20% for expert performance. So that's pretty good, given the variance of the numbers that you guys got when you were doing human experiments. Getting within 20% is probably just about as good as you can get by actually running a whole bunch of people. So, but a lot of things that you'd want to know for user interfaces aren't just expert performance. There's a lot of times you want to know, well, suppose somebody has to think about something. Suppose they actually have to figure out what to do. So GOMS is a higher level model, goals, operator, methods, and selection rules. And the key point of this is that it includes the time it would take the user to think about which method to do something and then to pick one. So if you're thinking about moving the cursor in a text editor, well, you can move your hand to the mouse and move it and click, or you could use the arrow keys, or you could, use the scroll wheel, or there's a variety of things you could do. Which one of those are you going to use? Well, the GOMS model would have the representation of these different methods for moving the cursor around, and then a rule, a selection rule that would say, if you're just moving a few characters, use this method. If you're moving a long way, use this other method. So you invent a set of rules that would then use to calculate that, and then they'd write all these down in a special language and give it a scenario, and it would calculate some numbers again. And Bonnie John, who's a former faculty member here, actually built this tool while she was here called CogTool, or Cognitive Modeling Tool, where you can show it a picture of your user interface. Here's the user interface. And then you can show it some tasks that you expect the user to do. So first the user is going to click here, then they're going to read this, then they're going to click on this other thing, then they're going to decide what to do, this and that. And so basically you give an example of all these tasks that the user will do, and it will tell you how long it would take the user to do that if they were expert users and having to do this method. So this is an amazing tool that you can just show a user interface to this tool, and it'll give you a number about how long it'll take somebody to do that. Pretty clever tool. It's available for you to use at this URL, and it's been shown to be very accurate, and they've used it for lots of different things. For example, they've used this for car navigation systems to say, we really don't want people to have their eyes off the road more than whatever the rule is, 2 seconds, 4 seconds or whatever. Can they do an operation on this navigation system quick enough so that they don't have to have their eyes away from the road, and for a certain amount of time? And so you could take a tool like this and go through every single operation in a nav system, which there might be 200 different operations you could do. And with a tool like this, it doesn't take too long to say, okay, are there any operations that take too long in this whole nav system? Whereas if you had to do a user study of all 200 operations, that would be really tedious, and your users would kill you because they're so bored with doing every single operation, right? So in a typical user test, you pick 4 operations, but to do all 200 or 600 would be really ridiculous. So with a tool like this, the tool doesn't mind. It's happy to go through every single thing. So there are lots of situations where this is proven to be really effective. Okay, I managed to get through them all. Kind of the general summary of these tools is there's a variety of things you can represent in these tools depending on what sort of questions you have. And often there's a really good way of making sure that you can evaluate the things that you want to evaluate and that you can have a complete coverage of the space that you're looking for. Okay, so Monday we're going to talk about text editing to get ready for the final homework 4, and then Jeff will be covering some more of this ergonomic stuff on the Wednesday. The following Monday, I think, is a guest lecture, and then the following Wednesday is the midterm. And so we'll have a lot more information about that soon, because we're coming up to the mid of the semester.